Yeah, I'm Stephan, and today I'm talking a bit about going from stream processing applications, from individual applications to a stream processing platform. This is it's a bit of a continuation of the talk or the presentation from last year's Flink Forward that I gave. We're talking a lot it was a closing keynote that we gave there about how stream processing is a paradigm that kind of changes the way we're building applications, and so this is all about going from this building blocks that allow you to build data-driven applications to a broader data-driven platform. So yeah, what do we mean when we say building a stream processing platform? The idea of a platform is to make building applications very simple, taking care of a lot of the common and repeatable parts, so that you focus actually on the development of the actual application, not on all the plumbing around. And when looking to build this platform, we're looking out into the world and talking a lot to people that were actually picking up stream processing and Flink in particular, and we're building such platforms. There are a lot of data platforms out there. There's all the platforms built around Hadoop. So what we saw is that still, to adopt something like Flink, to adopt something like stream processing, companies were building kind of a different form of platform. And we were actually lucky enough to find in all these companies people that were very open and very friendly and let us sit together with them and talk and say like, okay, what did you have to do in order to make this an easier or more lightweight, more repeatable thing to deploy a streaming application. So a big thank you to all the community, Flink community members from those companies that sat together with us and shared their insights. There may be two very high level conclusions that we had that kind of are a big reason why building a stream processing platform is quite different from building many of the like batch data platforms that are already out there. And the first observation is that stream processing is really it's a lot closer to building applications than it is to building classical like Hadoop Spark style data processing jobs. And that comes kind of with a different philosophy that we see in how stream processing or Flink is being picked up by different teams. It's very often actually different teams in the companies than the teams that do the batch side of the data. So yeah, well you can think of a batch data architecture is very much around first of all, having a good way of ingesting data and then a very flexible way to figure out what to do with it later. Stream processing is very much about building immediately on the data an application. So you're not just collecting it and trying to later figure out what to do, maybe store it in a most general schema-less form or so. But it's much closer to what the folks that build microservices, that build applications with Spring also actually used to do. And the second thing that has a very big impact on how we do things is the change to the I like to call it database-centric architecture that stream processing introduces. And you may actually recall this slide from the end of the last Flink Forward conference. So one of the very big changes in how stream processing, at least in the implementation of Flink, works, is that it doesn't work by separating compute into a stateless layer from a database that is responsible for holding all the data, taking care of durability, persistence, and all the tooling you need to do to evolve that over time. But instead, it actually takes the state out of the database, it puts it into the computation, and makes the storage layer something that isn't really synchronously worked with, but that is just used as something for asynchronous writes of large blobs in Flink's case, like producing result streams, writing snapshots. So that has quite a big implication on how you do things. So on the left-hand side, in the classical tiered architecture, you have stateless computation, and you cross the tier boundaries for every actually every data element you access. You can introduce a lot of caching, do a bit of lazy write-back and so on, but in principle, the picture looks roughly like that. On the right-hand side, in the streaming world, you almost pretend you're a standalone application, right? You work on your local state. It's almost as if you write a program that's just working with local variables. It's not concerned with actually making any remote changes and updates. And that is really nice for a developer because it immediately gets so many questions out of your way, both in terms of performance tuning, in terms of consistency models. You can just assume you're working as if you're just doing a local piece of computation of work, and then persistence becomes kind of an asynchronous background process, which is one of the really nice things that make Flink also suitable for high throughput workloads and so on. Now, while this is a really nice thing for the application developer, like the right-hand side changes the ops game quite a bit compared to the left-hand side, and that is one of the other big reasons why making something that is a platform for easy, repeatable stream processing application development to automate all the operational aspects of it actually looks different than it does look for classical application platforms. But nonetheless, it was actually a good idea to maybe first look at application platforms and see what do we see there, and then how can we start from there and see that we lift this to as streaming platform. All right, so maybe you can think of this as a very, very minimal skeleton of what many of these companies have built. There's some quite sophisticated resource abstraction layer, some integration with logging, metrics, CI/CD, of course, like alerting, and starting with something like that seemed quite reasonable. And the first thing we dug deep into was the resource management layer. Okay, on the resource management layer, it really seems everything is about containers these days, and Kubernetes has a very strong standing there. So we started looking at Kubernetes and its model and see what is there for us. How can we make use of that for a streaming platform? And Kubernetes has this really, really nice model. They have a bunch of containers, these greenish bubbles together in that are replicated stateful set or so on. And you deploy new containers or you modify existing replicated sets or stateful sets, change the number of containers. That way, scale in, scale out applications. Seems like a very nice model to start with. That represented really a lot of the operations we also saw and that people wanted to do. Now, where things got a little more tricky was when we started looking at how does that actually relate to the kind of stateful applications that we had in mind, especially with this architecture as outlined on the previous slide, not having this classical division. This model does in fact look, or it does work very nicely in this more traditional architecture, in this more separated architecture. You have the computation in your containers, you have your data in a database. If you just bring up a new application, you bring up a stateless container that just interacts with the same database, or you modify the number of containers of an existing application, and they just all interact with the database. There's really nothing that the addition of one container changes to another container. It's all stateless. Where things become a little more tricky is if you actually not assume stateless containers anymore, which is exactly what stream processing is about in some sense. And that's not only something that's specific to stream processing, it's actually something that's also relevant to a lot of other types of applications. So a more challenging scenario is actually the following. Just assume you're actually running a replicated database in your container infrastructure. Let's say everything is replicated 3 ways. And at some point you say, okay, we've done the whatever beginning of day, end of day spike of load, and for resource efficiency, let's actually just like shrink it maybe for the night or so. So we want to scale the resources by half, shut down 4 nodes. If we just do that naively, it's not gonna go well, right? If we just tell the system in a very simple way, let's just decommission 4 containers, then our database might not like that too much. Instead, what you typically have to do is you have to initiate like a more elaborate procedure, right? Have to call into some hooks, like decommission some nodes, stop accepting writes, start to migrate some partitions to other nodes, and then bit by bit decommission those nodes. So it's possible, but it's not quite as lightweight anymore as some of the other applications. And it goes actually even further. So when you first adopt an application, let's say a stream processing application with Flink, just rolling out the first version of that application isn't necessarily a tricky thing. What is more challenging is to start to think through those aspects, and those are parts that inevitably come with every application that runs for a longer time. So stream processing applications aren't like a batch job, right? You don't run them every night, and from this night to the next night you might switch maybe a configuration in a jar file, and then next time you run it, everything is it's a new version. It's a continuously running, it's an always online application. So you have to do these things a bit different. And let's look at all of those questions here, and how we can actually approach them. Doing a stateful upgrade in stream processing. If you just want to upgrade let's say a stateless container, there's a ton of tooling. Just do like a rolling upgrade with different versions. You're going to bring up some new containers, a new version, decommission some old containers, and so on. Ideally, there's a common database schema that for the time while you have the 2 different versions running, that both understand, and that's actually good. Once you actually upgrade a stream processing application, you have to think almost more in the way of upgrading the database itself, right? Because you're not just upgrading the stateless computation, you're actually upgrading the part that manages all your application state. And the database upgrade is significantly more involved than just like rolling out a new set of stateless computation containers. But now that we kind of broke with this 2-tier architecture and said state is part of the application, we actually have to do this way more often. So we need a good answer to this, right? Otherwise, we just did something that is really nice for the application developer, but it's going to be very hard for the operational side of things. And we, in the spirit of making it really easy to write applications, of course, we don't want to force every stream processing application developer to also be able to work in a rolling upgrade fashion, have maybe 2 schemas of the state online at the same time that both versions can share, and so on. We need an easier answer to that. The other part is trying to actually migrate applications. Let's say we have a staging cluster or a testing cluster, and we have a production cluster. And at some point in time, we've done all our testing or acceptance testing on the staging cluster. We want to move it to the production cluster. This is just, it's a bit more now than just launching the containers here, because again, they're not just connecting to the same database, but you actually have to almost migrate the database to the other environment as well. And this list goes on. Reprocessing and reinstatement is something that happens easily once you start running a production for longer, and you inevitably at some point introduce an application level bug or so, and you have a set of corrupt results and you need to fix them, or you need to evolve your schema at some point in time. And this is now, in some sense, both easier and harder to do. Easier because you just evolve the application as a whole, you evolve it with a state, and also harder because, again, it's like you have to take care of the database side of things. So the good news is that stream processing as a whole, and Flink in particular, has actually very interesting answers to all of those questions. And that led us to the point of actually saying, okay, if we take something like Kubernetes as a starting point, container-based resource orchestration, together with Flink, stream processing, and very importantly, Flink's capability to draw these consistent distributed snapshots of application state, and we add we add a component here that kind of ties these things together in a very nicely integrated way. The statefulness, the snapshots of Flink together with the container orchestration, config management, and so on. Then what we get is actually a very nicely working container-based platform for stateful streaming applications. And you can almost think of this component, this application manager, as a very natural citizen in the Kubernetes world. Similar as if you run Helm or if you implement a Kubernetes operator, it's a thing that itself runs in Kubernetes, but it helps to lift the abstraction level of the whole thing and level up to actually let you think about things in a slightly higher level abstraction, and just take care of a lot of things underneath the hood for you. So that is actually what we added here. In this platform, we have our set of containers provided by Kubernetes. We assume some form of bulk storage that we can use for to archive snapshots from Flink's side. And then this component, this application manager, is actually the bridge between the application, the operational side of things, your CI/CD chain, or just your developer that says, I want to just push out a new application via a REST interface or a web interface. And it really takes care of making all these things go nicely together. So for example, if you actually have a set of containers and you want to just scale it up or down in a very easy fashion, what it actually does is it integrates, calling into Flink's snapshot mechanism to actually draw a snapshot, bringing up new containers, repartitioning the snapshot, bringing it up. If you say, okay, I actually want to migrate this application, let's say from a staging cluster to a production cluster, what it will actually do is, will again call into like a snapshot, in Flink snapshot method, roll out a new set of containers, migrate the snapshots, and kick this whole thing off. So in some sense, what you get from this is an abstraction level where you're not thinking in terms of Flink jobs, save points, jar files, configuration files, and so on. But what you actually get is applications with multiple deployments, multiple versions that you can basically switch with, almost like in a application level version control system. So let's say we're rolling out an application version 1, starting with some code, some configuration, and maybe empty state, or maybe we start with a state of another application. We just say, okay, pick up the snapshot from this experimental run, use it as a starting point for this production run. You can just modify the deployment and say, okay, actually just change this thing here to use different code. What it will internally create is a new version of the application. It will give you a distributed snapshot of the old application containing configuration, code, and the state at the point where you made that change. You can upgrade it another time. You can say, okay, here's something interesting happening. Maybe something either good or bad happened while we were running in version 2, and it's time to look into this a bit deeper. So let me actually just clone that version, and you're basically just duplicating the Flink job. Have pretty much two identical copies of that thing running. Could be on the same, on the same cluster, could be on a different cluster, and then you can actually independently evolve those. So it's and you don't have to worry exactly about all those questions that I outlined there before, like scaling up and down containers. What do I do if I scale away too many? Like what happens with the what happens with the state? If I actually create those new containers, are they stateless or stateful? If they're stateful, what should be their their initial state? All of those things are basically they're just abstracted behind that level. So that is a very it's a very elegant way of thinking about stateful stream processing application. So the thing as a whole looks actually like that now. Based on a container platform, Flink as the API to develop applications, and then the application manager is kind of a proxy between the operational commands and Kubernetes and the snapshot store and Flink to kind of orchestrate all these things working tightly integrated together. All right, if time permits, I can try and just do a very brief demo. We have a few more minutes. This is going to be just an extremely quick look at how how this might feel if you use an abstraction like that rather than independent Flink jobs. We have a booth up there, so pretty much, I think after the keynotes are through in the first coffee break, we're going to have a series of demos and like more deep dives there, where you can actually see a little more of what is happening behind the curtain there. There's also a dedicated talk later today that basically explains a few more of the technical details behind the system. All right, just very briefly. The scenario here is we have some form of application that, in this case, I'd say orchestrates payments across Europe, and it's running here. This is not part of that's not part of our platform. That's just like it's a Kibana dashboard that visualizes some results. And this application it's a continuously running stream processing application. And what we see here is apparently something is not quite right. So this greenish curve that just dropped down to 0 just looks like it's not quite right. And if we dig deeper, we'll actually see that Germany is actually not getting anything through these days. So we have our continuously running application, and apparently we do have a bug in there. So what do we need to do? First of all, we need to obviously fix that bug. So let's just assume the coding part of that is done for the sake of time. And what we now need to do is we need to upgrade it. And the upgrade here is it's one of those stateful streaming updates that you need to do, right? You need to replace the code, but at the same point in time, you need to see that the new containers that you launch with the new code that you launch actually carry forward in an exactly once fashion the state from the old containers, right? So we and it could actually potentially be that we're in the course of doing this, we're changing some wire format, we're changing some like state formats and so on. We still want to be able to migrate this all in a seamless fashion, and so that's actually the first thing that we do. So we're starting with this application manager here, where we have this particular deployment of this streaming application running. And we're now changing it. Some friendly developer actually told us, okay, they have actually created a fixed version of it. So we're just going to change the whole thing. We're starting on a basic Flink image based on Flink 1.4, Scala to 11. This is the application that we actually package into that container and that we run. And then we're patching it, and what we can see is that this thing will actually it will create a new job. It will trigger a save point on the old one. It will spin up a new cluster, and then it will basically transition this new one to actually replace the old one. So we can see all these events happening here, waiting for new containers to come up. All right, and if everything goes well, we should actually see that the bubble here reappears. Okay, so everything is fixed. And we also see that, while this one bar is now going up and saying, okay, we're actually processing all the events correctly for Germany anymore, we don't see a break in continuity for everything else. Everything else is just like, everything is fixed. We have a consistent snapshot that was carried from the old one into the new one, and we applied a patch on the fly. And, this all together, this made sure, like in one kind of atomic operation, tearing down the old application together with a snapshot, bringing up a new application, migrating the state, migrating the code. All right. Now, if we look at this thing here, we actually see like, yeah, okay, it's getting fixed. This is more like a 3-hour average, so the bar still hasn't made it all the way up. But we also see, okay, there's still something in the past, right? There's still corrupt data in there. So we've actually fixed the real-time side of things, but there's still, like in the history, there's still problems. So here's where the other part that they were talking about, like reinstatement, reprocessing, and stream processing comes into play, right? We can actually see here that that this thing keeps the different versions for us, keeps the different snapshots of Flink as a whole. And we can see, I'm not sure if you can see that, it seems kind of blurry here, but when we actually changed the latest deployment to fix the bug, we actually got a new snapshot of the entire application in here. So we do have actually a new version of this whole thing. So one way to actually, keep in mind, we have stream processing paradigm here. We have our events kind of all logged up. We have, exactly once processing inside the application. The state is all inside Flink. So one way to actually fix this would just be to say, let's actually take the code that is doing it correctly and just like reapply it on all the data of the past. And that way we can, we can just make this thing work well again. So what we can do here is just say, take this application and reset it to this prior save point, which is basically take the latest, let's say take the latest code version of the application, but take a previous data snapshot of the application and just use that to, to rewind it and reprocess everything. So just take this particular snapshot. It actually will tell us, okay, I'm taking the previous one, I'm kind of soft linking it to be the latest one. You see that, up there's, it's actually going to like reinitialize all the containers and so on. And yeah, so if we see this dashboard here, I think we have to give it a little bit. The snapshot was taken quite a while before the bug. Give it a few seconds or so. And it will just start to bit by bit like reprocess the data of the past with the latest code version and just like fix all the computation. Those are just a few things that you can actually do once you have adopted this like a stream processing paradigm, and you have a tool like that actually allows you to think not in terms of just individual Flink jobs where you have to figure out what's the state supposed to be, where do I have to subscribe to here, what is my latest save point, how does these things go together and so on. It's just like it's a very easy way of just thinking in terms of versioned application. So what we basically did here is we first upgraded it, and then what we actually did is we soft downgraded the state of the application to the previous one to actually trigger to reprocess it while keeping the latest code and configuration version, for example. So you have a lot of flexible ways to kind of play with that. There's a bunch of other really cool things that you can do with that. So for example, we could have said, here we go. Okay, thanks. So another thing that we, for example, could have done is we could have said, instead of like rewinding the real-time side of things, we just create a fork and use a fork to reprocess the history, so that we keep the real-time application running real-time and we don't impact it in any way. We just create a snapshot copy of the past and use that to have a copy to reprocess things. And there are even more ways you can do this, like very, very flexible ways of dealing with all these situations. And if you're interested in that, come to the follow-up talk or to the demo that we have at the booth later. So with that as a starting point, container-based, like stateful container-based resource orchestration for stream processing, what would the future of such a platform look like, or what are the next things to think about, right? So this is the way we think about this is really the essential building block, right? This is, for us, it's kind of Kubernetes lifted to the right abstraction level for stateful stream processing. There are a few definite check marks that such a platform needs to have that we're working on right now. Proper role-based access control for multiple teams to work with this, more sophisticated metadata management, and of course disaster recovery cross data center failover. Again, for cross data center failover, actually the snapshot model that Flink has in itself, Flink's checkpoint model, is actually an extremely powerful tool to implement very flexible failover strategies based on how much in sync you can afford your data centers to be, how much your cross data center traffic how much cross data center traffic you can afford or you're willing to pay for, and so on. So they're very interesting models to do that. Beyond beyond those things, there's a few things that I find personally very interesting to think about going forward. We're talking a lot about stream processing, but there's also the other side. Flink is definitely also a batch processor. Thinking this philosophy of everything streams, batch as a special case of streaming, how does that fit into that world? And it actually fits very well, right? Finite applications can be just a special case of continuous applications. You can actually start finite applications from a snapshot of an infinite application that's running somewhere in the middle or so. That actually fits perfectly into that world. Stream processing. There are quite a few industries that really like the idea of stream processing, continuous processing, but just happen so by the nature of that industry. Events just don't come evenly all through the day. It's just like there's an end of day kind of thing that where most of things happen. And it's really nice to model things as stream processing because you don't have to chop it into batches and to worry about the batch boundaries and everything. But actually just running it all the time for the 1 hour end of day that you're actually doing work is kind of might be a bit prohibitive. And actually doing like a bursty way of stream processing, just starting and stopping these jobs, bringing them up from a snapshot, let them run for a while, suspending them with a snapshot. Like, think of it as a stream processing with a bursty execution. That's for example one way also to get like a batch processing as a special case of stream processing into such a platform. I want to give a quick outlook because one of the next keynotes is in some sense doing a nice continuation of this story here, and that is a streaming data platform definitely needs to cater to a very broad audience of developers, right? And the way things have started in most systems and definitely also in Flink is you start in the JVM, you start with Java and Scala, the two, obviously the two most popular JVM languages, but that kind of excludes a lot of your developer audience. So what about languages like Python? What about languages like Go? What about other languages? There are a lot more in the world. There are many more developer communities, and Anand will actually speak about this in a lot more detail in a few minutes. Beyond just broad support for developer audiences by supporting many languages. At some point in time, all of these application platforms started to kind of add, like support for more specific use cases. What we have today in Flink is SQL and CEP. What we're seeing coming up more and more is also, dedicated libraries for machine learning and others. So think of the languages as being a way to broaden up the whole platform towards more developers. These libraries being something for specific use cases to make it easier for these common patterns, and all of these things are basically what in the end makes a good streaming platform this powerful piece that gives like easy repetitive application development where you don't have to worry about these hard parts. Just assume those things are taken care of. Yeah, with that I'm actually done with this presentation. Like I said, stay here. There's like the next presentations almost continue kind of on the theme of this, and if you're interested in to learn more about this whole like stateful streaming platform, container orchestration, and so on, in the next coffee break there is a demo and there is a dedicated talk this afternoon. Thank you very much.